All right. So we're the Boston Computation Club, which we just plagiarized the name from the London Computation Club, which is a fun little club in London who provided a lot of notes that I found useful when I was taking Amal Ahmed's class on programming languages. And we host talks on a variety of subjects in math and computer science. We're not really highly focused the way that some groups, such as, for instance, the Topos people are, but we do a lot of different fun things. And if you're interested in kind of graduate level topics in computer science and math, I think we're a fun group. And this is a good example of the sorts of talks we host. Right now, everything's remote, but we'll start doing some in-person events in Boston once it's safe to do so, and we're all kind of back in the same place. Anyway, today we have Carlo coming to talk to us about homotopy type theory. And I'll just say I'm very excited about this because homotopy type theory is really one of the things that got me interested in formal methods. I did my undergraduate degree with Sean here, but also with our buddy Chris Brown, who some of you know on Twitter. And we would go get lunch occasionally, and he would tell me about homotopy type theory. And it always sounded cooler and flashier than whatever we were doing in class. I know nothing about it, although I know some homotopy theory and some type theory. So hopefully Carlo will kind of connect the dots for me here and for all the rest of you. And with that, Carlo, take it away. Thank you so much for joining us.
Yeah, well, thanks for having me. And I'm doing something new for me, which is trying to give a Beamer talk on my iPad. And that's so that I can just write, since I think we'll have plenty of time for questions. So I plan on this talk being about half an hour long. So there'll be plenty of time to ask things sort of in the middle and also at the end.
Perfect.
So, okay, great. So without further ado, all right, I wish it didn't have that transition, but anyway, so what is homotopy type theory? Well, in short, it's a version of dependent type theory, and it's interesting because it fixes a bunch of equality issues that equality has in dependent type theory, and it does that by adding some features called univalence and higher inductive types. And the reason why these features are good is, in short, that they endow more types with universal properties. So basically, the goal in this talk is to just explain what this slide means. And I'm going to start by just recalling a little bit what's going on in dependent type theory. So a dependent type is a type that can depend on a term, right? And so what that means in particular is you can write things like, a type of lists, not just any lists, but that have a specific length n, right? So this lets you capture more specific invariants, like that sorting a list doesn't change its length, or that if you concatenate two lists, the length is a sum of the input lengths, or that if you are trying to take the first element out of a list, it has to be non-empty. But you're not just limited to arithmetic like addition. You can also write sort of more complicated things. So if you have a function that removes the first instance of a number from a list, then what is the length of the result? Well, if that element is in the list, then the list gets one shorter. Otherwise, it stays the same length, right? Okay, so what happens if we write the program that removes the first occurrence of 5 from the list 4, 5? Well, in theory, this should produce a list of length 1. So this program should have the type list of length 1. But if we just look at what the type of remove is supposed to be, and if we just plug in 5 and 4, 5, we'll see that actually, officially, the length of the list is if 5 is in 4, 5, then 2 minus 1 else 2. Okay, and that's not really what we wanted. But fortunately, we can see that this if expression is just, it's a program, so I can run it. I can see that it evaluates to 1, and then the type checker will say yes, okay, because this evaluates to 1, it's fine to just say this program has type list of length 1. So for that to work, the type checker is actually running programs during type checking. But that's not good enough. You sometimes need to give it some help. So if you want to write a function that takes a non-empty list, and then it sorts the list, and then it removes the first element of the original list from that sorted list, Okay. In theory, this function should take a list of length n plus 1 to a list of length n. Right? But again, officially, the type of this function is this much more complicated thing. And here we can't just rely on computation. Right? Why not? Well, because L is a parameter. I mean, this is a function. I don't know what L is, so I don't know what this evaluates to. So I can't just evaluate this if expression because it doesn't evaluate any further until I have an L. But I mean, you might say, well, okay, I just happen to know that no matter what list I plug in, I mean, this condition will always evaluate to true, right? Because I mean, there are a number of ways to see that, but for example, sort always just permutes the list. So whatever the first element was beforehand, it will still continue to be somewhere in the list. So this will evaluate to true, and you can prove that as a theorem. And if you prove that, then you can say, well, then this will evaluate to true. So this if expression will evaluate to n, right? And so we can actually insert a sort of cast here that says, using the theorem, I can cast this complicated type to the type list n because I've proven that those will always end up being the same thing. Okay, and so the power of the type theoretic proof assistance really comes from these two kinds of equalities sort of working together all the time. There's this sort of computational aspect of things where the type checker is always symbolically executing the code that occurs in types to simplify them as much as possible. On the other hand, that doesn't always get you where you want to be, and in those cases, you can prove equality theorems, and you can use those to typecast. Like in the second example. So there are a lot of different names for all of these things. And the things on the slide aren't all exact synonyms because, I mean, it turns out dependent type theory is pretty complicated. But for the purposes of this talk, you can kind of imagine the computational equality is also called judgmental or definitional or silent or strict. The other kind of equality that you have to prove a theorem about and cast, that's called propositional or the identity type or weak. So you may have heard of these terms before. That's kind of what they mean. And when I say typecast, really what I'm talking about is that whenever you have a proof that two types are equal, then you get an isomorphism between those two types. What that means is that you have a function from A to B and you have a function from B to A. Those are the sort of casts. And those two functions cancel. So if you cast one way then the other, that's the same as doing nothing at all. Okay, so then the plan for today is to first talk about universal properties, which are, I'm going to spin that as basically how to see when things should be equal, either weakly or strictly. Then I'll talk about Voevodsky's univalence axiom, which is the universal property of the universe of types. Then I'll talk a bit about higher inductive types, which are a generalization of quotients. Then I'll close by talking about some applications to computer science. But this is a good point if anyone has any questions right now. Feel free to ask. Okay, universal properties. So the way we can think of type formers, like product of types or functions between types, you can think of these as bundling up multiple pieces of data into a single object. So to understand when these two complex objects, two elements of these more complicated types should be equal, what we can do is we can look at when the corresponding collections that they sort of are bundling up, when those collections are equal, and that will sort of tell us what the equality of the more complicated type is supposed to be in some sense. So let me just look at a simple example. If you have a product type, so externally, if you have a term of type A times B, then you can project out two components that will give you a term of type A, and they'll also give you a term of type B. Right. On the other hand, if you have a term of type A and a term of type B, you can pair them together, and you'll get a term of type A times B. So you have functions going back and forth. But you don't just have functions going back and forth. They're actually an isomorphism, which means that if you go one way then the other, these functions are going to cancel. So the one way, if you're on the right, you go to the left and then back to the right, those two things canceling are the beta laws for the products. And the other direction is the eta law for the products. And the eta law, I just want to point out that the eta law says not only for, for pairs do you have these maps cancel, but actually for any element of A times B, including a variable of type A times B. So that's where you get a sort of eta expansion of variables, if that means anything to you. And if it doesn't, that's fine. All right, so why is that good? Well, the universal property of the product basically tells us that having one thing in the product or having two things in the constituent types, those are exactly the same notion. So, for example, you can curry or uncurry as much as you want. It doesn't change what you can prove because these two concepts are the same concept, right? And now for certain types, these universal properties hold strictly. So for products, beta and eta can usually be handled sort of fully automatically by the type checker in a lot of type theories. But some other universal properties are going to only be weak, by which I mean you'll get the ability to cast between these two collections, but they're not actually on the nose the same. So for example, that's how functions out of the natural numbers work. So the universal property of the natural numbers is basically that, if you have two functions out of the natural numbers that are the same on every number, then they're the same. But that's not something that you can ask the type checker to like symbolically figure out that two functions nat to nat are the same. You can't have that automatically, so we have the next best thing, which is to have it weakly. But there's some other universal properties that are actually missing entirely, and that's kind of what the rest of this talk is going to be about, and how we get them back. Okay, so an example of that are the so-called characteristic functions. So in most type theories, we don't actually have a way to talk directly about the subsets of a type. Sometimes you do, but usually you don't have a sort of subset type former. And instead, if you ever used one of these proof assistants, what you can do is you can talk about predicates on the type. So you have a function from A to propositions that says whether or not the element of A that you have in your hand is in the subset or not. So you can define a predicate that checks whether a number is even. Okay, and then using that, you can define the type of even numbers by just saying an even number is a pair of a number and a proof that it's even. Now, in set theory, so I'm not talking about type theory for the moment, we have a universal property for these characteristic functions. Namely, there is an isomorphism between the subsets of a set A and the functions from A to prop, where here prop is just the Booleans. True and false. Okay, and these so these two things are isomorphic in set theory, but in type theory, well, every type theory sort of every proof system has a slightly different version of prop, but in any case, this usually doesn't hold. And the reason why it doesn't hold is that the equality of functions A to prop is wrong. So basically, this side is the wrong thing, so you don't get an isomorphism here. It's actually wrong in multiple ways. So first of all, you don't have something called propositional extensionality, which is the principle that if you have two propositions and they're interprovable, then they're the same proposition. Okay, you have that in set theory, but you normally don't have that in type theory. The other thing is called function extensionality. So you also don't know that if you have two functions from A to prop and they agree on all elements of A, then the two functions have to be the same. Right? So actually, both of these things don't work. And as a result, the equality of functions A or a prop is sort of too fine. So it doesn't coincide with what the equality of subsets of A is. And so as a result, you don't have this universal property. Okay, so now I'm going to talk about fixing that. So again, if there are any questions, feel free.
Hey, let me just say, if anyone has a question, go ahead and unmute and ask. We're not like following like Oxford style rules or something here. We're all dirtbag grad students. You can go for it.
Yeah. Well, I'll move on for the moment. So with all this in mind, what is univalence? Well, again, you might not be surprised. Univalence is, again, another sort of universal property. And what is it saying? Well, it's actually saying that whenever you have two types, well, okay, so in type theory, you, like I said before, you normally have the principle that if you have a proof that two types are equal, then you have this transport function that gives you a way of casting between them. So you have an isomorphism between those types. You can go from one to the other and vice versa, and those functions cancel. Univalence actually says that there's a universal property here. So not only do you have a function from the left to the right, but actually these two collections are isomorphic. So you have an inverse to transport, and these two things cancel. So you can sort of think of univalence as the universal property of the universe, or which is jargon for a type of types. I'm going to call it type. Okay, and people often sort of shortcut univalence by saying it means that isomorphic types are equal, which is true, but I mean, it really what it means, to be fully precise, it means that there's a universal property here where these two collections are isomorphic by an isomorphism like this. Now, this principle is actually pretty subtle though, because there can be multiple different isomorphisms between the same two types. So for example, if we just look at functions between bool and bool, there are actually two ways that bool is isomorphic to itself, by the identity function and by the function that swaps the two points of the booleans. Okay, so and these are different because the functions do different things. And so as a result, there actually have to be multiple different ways of seeing that the Booleans are equal to themselves, because the collection of isomorphisms and the collection of equality proofs are the same, or they're isomorphic. So there have to be multiple different proofs that bool equals bool. And this actually induces sort of an infinite structure in the following sense. Well, you can have two types that can be equal in more than one way, P and Q, but the proofs P and Q can themselves be equal in more than one way, H and K, and so on all the way up. So you sort of get these, points, paths, paths between paths, and so on. And this structure actually behaves very much the same way that paths in a topological space behave. So that's sort of where the name homotopy type theory comes from, that when you accept univalence into your life, types sort of turn into having this homotopical structure that they didn't have before. So actually, there's a very important idea in HOT, maybe one of the most important ideas. It's called homotopy level, or H level, which is that you can stratify types by where this structure stops existing. Because, so I said, in general, you have this infinite structure, but for any particular type, usually the structure stops, it sort of stabilizes or trivializes at some point. So for example, a normal type is an H set, which means that, okay, it may have a whole bunch of different elements, and those elements are equal to each other or not equal to each other, but any two equalities between the same two things are equal. That's what an H set is. But you could be even less interesting than that. You could be an H prop, which is not only are any two equalities the same, but any two elements are the same. Conversely, you could be more interesting than an H set, something called an H groupoid, which is equalities can be the same in more than one way, but any equalities of equalities are going to always be the same. So again, this is about just how far up you have to go before the structure stops being interesting. Was there a question? Yeah.
I had a small question. So in the example from before with the bools, where there's two ways where bool equals bool, so would that be like how does that sort of map into these three properties?
Yeah, so right, good question. So bool itself is an H set, but the universe that it's in is not an H set, because by univalence you have bool and bool, that are equal to each other in two different ways, the identity function and the swap function. And in fact, the best example of a type that is a very complicated H level is the type of types. So the type of types has a very complicated H level, but and the exact, so I'm being cagey because the exact H level of type depends on what things are in it, because that affects how many ways its elements can be equal to themselves. So let me just say that if you have a universe that includes bool, it's at least not an H set. It's a H groupoid or worse. But bool itself is an H set. Does that help?
Yeah. And then I guess the follow-up question would be, so is H level basically like, how is that connected to like the kindness of a type, I guess?
Like in terms of how many connectives it has or something, or like, or how, yeah, being a function between types.
Yeah. Or I mean, just, not a PL person here. So just a former Haskell. So like it's like kindness, I would assume is like where it's like the level of higher orderness of like a type.
Right. So you actually get these sort of two orthogonal like levels of stratification. So there's size. There's one thing that's like the size of the type, but then there's another direction which is like the H level of type. So yeah, you actually get a whole two different sort of hierarchies.
Cool.
Okay, so all right. Okay. So univalence is really good. It's very powerful, and it's not really easy to see that directly why that is, but maybe to give you an idea, let me just say informally, it's a very powerful universal property because the universal property is itself about isomorphisms, and all universal properties are about isomorphisms. So it's kind of like a universal property that's about universal properties. Okay, I mean, that's not precise, but I think that's, there's a sense in which that makes sense. But basically it's sort of a universal property for universal properties. And as a result, it actually implies a ton of other universal properties. So for example, it implies propositional extensionality for the collection of H props, which was the fact that if you have two propositions that are interprovable, then they are equal. It also implies function extensionality, that if you have two functions that are pointwise equal, then they're equal. It also implies the principle of unique choice, which says that functions are the same as functional relations, which I mean like binary relations such that for everything in the first component, there's one thing in the second component. So it's sort of the ultimate universal property that implies tons of other universal properties, including all the ones I mentioned so far. So maybe let me pause here and just say where these ideas came from. So the idea that that equality in type theory sort of has some interesting iterated structure goes back to 1998, something called the Groupoid model. And the idea that it actually has an infinite amount of non-trivial structure goes to about 2006 by Audi and Warren and some other people. Around the same time is when the mathematician Voevodsky developed the univalence axiom. A few years later, these things called higher inductive types came along. And then there was a special year at the Institute for Advanced Study on hot and univalent foundations that led to this book that's on the right that you might have heard of, that you can get online. It's a good resource. It's sort of the first resource and still a very good one for learning more about how hot works. And ever since then, well, there's just been a lot of stuff going on. And a lot of people in both math and computer science have been working on various aspects of homotopy type theory. So what are the mathematical applications? What can you do inside of homotopy type theory? Well, there are kind of two main classes of things. I mean, I'm oversimplifying, of course, but there are kind of two main classes of things you can do.
Carlo, I think we might have lost you, unless the issue's on my end.
But yeah, okay, you back? Okay. The idea of univalent foundations is that you redo math, but replacing sets with types. So you're just in a setting where the sort of basic objects of the theory, the so-called sets, satisfy univalence, but you're not trying to do homotopy theory specifically. So why might you want to do this? Well, it's sort of better than doing math in normal type theory because it has all these additional universal properties. It's also sort of better than doing a normal math, so to speak, because it's, first of all, you can formalize it more easily. And second of all, because the univalence axiom guarantees that everything you do is invariant under isomorphism.
Hey, Carlo, I think I missed something really obvious, and maybe this is a good time to ask. Did our paths just kind of look morally like paths, or did they actually exist within a topology? And what was that topology?
Yeah, so there's not actually topology. It's just there's just homotopy.
Okay.
So there are other versions. Maybe we can talk about it later. But there are other versions of type theory of HOT where you try to surface not just the sort of homotopy theory of spaces, but also like continuous aspects or differential aspects of spaces, things like that.
Okay.
But yeah, here it's just homotopy theory.
Okay, that makes sense. Yeah, since I've only done undergraduate topology, I hadn't seen homotopy outside of that context. So that makes more sense now.
Right, right. So basically, you can, one way to study homotopy theory is sort of analytically, so to speak, where you say, okay, I'm going to study like what paths look like in topological spaces or like well-behaved topological spaces. But you could also do it in other settings, like in, you can study what paths look like in simplicial sets instead of topological spaces. Or you can study synthetically, you can study what do paths look like, but in type theory with the univalence axiom and so on. So these are all sort of like different versions of getting at the same sort of homotopy theory. Okay, great. So the last sort of feature of HOT is called higher inductive types. And these generalize data types or inductive types to allow for constructors not only of the type itself, but of the equality of the type. So if a normal data type is something like the Booleans, where you say I have two constructors for the Booleans called true and false. A higher inductive type might be something where you say, okay, I have two constructors, point and point prime of the type, but then I'm going to also throw in two constructors, eq and eq prime, that are equations between point and point prime. Okay, so it looks like eq and eq prime. Okay, and you sort of get the free type with point and point prime and eq and eq prime. And as a result, you can actually use univalence to show that eq is not the same as eq prime. So this isn't just saying I have 2 points and they're the same point. You're actually throwing in some amount of non-trivial structure. And the reason why I called it the circle is that you can actually prove, again, using univalence, that that this actually looks like the circle in some sense. It can be made precise. Like, for example, you can calculate the winding number of any paths in this type, how many times you go around the loop. And higher inductive types are very important if you're trying to do synthetic homotopy theory, because this is sort of the source of concrete spaces to prove things about, like if you know what a CW complex is, these kind of play the role of those. But they're also important if you're not trying to do synthetic homotopy theory. So for example, they let you define set quotients. So if you have any type and any binary relation on that type, you can define this sort of set quotient higher inductive type. I'll call it A mod R. And the constructors are, first of all, for any element of A, you get an element of A mod R. That's the first one. The second one says, anytime you have a proof that two elements of A are related by R, then the injections of those two points are equal in the quotient. So if RAB, then you have in A equals in B in A mod The third constructor is sort of, maybe you weren't expecting it. And this makes sure that the higher dimensional structure kind of gets cut off. It makes sure that that A mod R always ends up being an H set. So it says that whenever I have any two points in the quotient, and I have any two proofs that those points are the same, then those two proofs are the same. So this constructor guarantees that the quotient that you get out is always going to be an H set. Now, as in set theory, but unlike as in many versions of quotients in type theory, these quotients satisfy, again, a universal property. Okay, and I'm done saying universal property now, but they satisfy a universal property that's sometimes called effectivity of quotients. And in particular, what this says is that if R happens to be an H-prop valued equivalence relation, then you get an isomorphism between the proofs that A and B are related by R and the equations of in A equals in B in the quotient. So of course, you can go from the left to the right using eq. The eq constructor just goes from the left to the right. But using univalence, you actually get an inverse to eq, and these things are isomorphic. Okay, so to close, I just want to sort of circle back around to computer science, say, so, what does this mean for me? Well, like I said at the start, when you're using dependent types, you often have to prove equations to cast along the equations to give things the types you want them to have. And of course, if you want to prove that things are equal, this often requires, developing some amount of auxiliary theory or some kind of mathematics, like, you have to prove some discrete math or something like that. Now, in ordinary type theoretic proof systems like Agda and Koch, to pick some examples, many more involved formalizations actually have to use something called setoids, which are basically that you get rid of you don't use the built-in equality of the type theory, but instead, every time you have a type, you instead carry around a type paired with an equivalence relation on that type. And then everywhere you kind of manually prove that everything you're doing respects the equivalence relations that you're carrying around. By doing this, you can sort of set the so-called equality of every type to be whatever you need it to be. That's sort of the benefit of having setoids. And so in that way, you can sort of fix many of the problems that I mentioned before. But you don't get anything for free anymore. I mean, the normal equality has a property that everything respects it. But if you're using setoids, you manually have to carry everything around. It's very laborious, and it's also error prone. So the benefit of using hot would be that then you can just use the built-in equality, and it won't have a lot of those issues. You'll have quotients, and you'll have propositional extensionality and function extensionality and so on, without needing to sort of roll it yourself. There is a catch. So I've kind of only said good things so far. So, well, there are two catches. The first catch is, like I think I mentioned before, you have to be a little bit careful when you define things to make sure that they have the H level that you want them to have. For example, you have to pick a definition of isomorphism that is an H-prop, because if you define it the wrong way, it might not be an H-prop. But the other catch is, well, where do we get a proof assistant for homotopy type theory? Well, what people did at the start was they just said, okay, well, let me take a proof system for like normal type theory, like Koch or Agda or Lean, and to these we just add a bunch of postulates, which are basically these constants that will assert that univalence holds, or that we have higher inductive types. So for example, if you want to assert that univalence holds, you can just add these two constants, and then you'll have univalence. The problem with this is that these constants are so-called stuck terms. And what I mean by that is, transport inverse is supposed to be a function, but if you pass in an argument, you didn't actually implement the function, you just said there is some function. So it won't actually do anything. So if you write transport inverse of f, that will just stay there. It never gets simpler than that because we don't know what transport inverse does, so to speak. So the type checker can't help you out. So, the symbolic execution never gets to simplify transport inverse for you. And that ends up kind of being a problem. The more complicated the things you're doing are, it's really helpful to have the type checker, evaluating things for you. And when things don't evaluate in that way, you sort of end up carrying around bigger and bigger proofs everywhere. It gets sort of more difficult to use. So cubical type theory is a way of fixing this. It's basically, it's a dependently typed programming language that has univalence and hits as features. So one way of looking at it is it provides an implementation of the constants that I asserted on the previous slide. It tells you how to run transport inverse. If you want to try out cubical type theory, there's sort of two main proof systems I would point you to. The first one is called cubical AGDA. If you have a new enough version of AGDA, you can just use it, AGDA-cubical. And this is based on something called the CCHM cubical type theory. And if you want to see, if you want to look at the standard, there's sort of a standard library for it that's in development right now on GitHub. You can find it there. And there's another cubical type theory called RED-TT. It was developed by me and many of my colleagues, including John Sterling, Favonia, Evan Cavallo, Bob Harper. And this is based on a different flavor of cubical type theory called Cartesian cubical type theory. But I'm not going to get into the differences right now. So just before I end, I want to kind of point out two sort of interesting applications. And like I said, you should sort of think of HOT as not needing some really weird application. The application is just that math works better. But if you want to see some examples of like things you can do when math works better, one is called HotSQL, which is in the same way that characteristic functions work. So functions from A into H prop sort of behave like subsets of A. In fact, when you have univalence, you can also see that multisets on A and functions from A to H sets work the same way. So you can represent multisets as functions like this. And using basically this idea, they don't do precisely this, but something very similar to this, the authors actually formalize the semantics of SQL queries in Calc with the univalence axiom using this idea. And they actually built their formalization into a tool that can verify the equivalence of SQL queries. And the other example I wanted to point you to, and apology for the self-promotion, is something that I worked on recently with some collaborators about getting representation independence in cubical type theory. So representation independence is this sort of classic PL idea that says that if you have two different implementations of a data structure, then you can always swap one with the other so long as they're equivalent in some very weak sense. There has to be some sort of correspondence between the two implementations that respects the operations in the interface. Now, these correspondences in practice are rarely isomorphisms. So you can't just use, you can't use univalence to just say, okay, well, now I can interchange to equivalent data structures inside of HOT. But what we noticed is that that these correspondences actually give rise to a way to quotient both implementations that are in the correspondence, such that these implementations actually do become isomorphic, and the isomorphisms respect the interface. And using this and using the univalence axiom, this actually allows us to interchange these quotiented implementations inside cubical AGDA. So we use this to, for example, replace two implementations of queues, replace one implementation of a queue with a more complicated one. Okay, so that's all I have to say today. Feel free to ask plenty of questions or hit me up later on Twitter or whatever you want. If you want to learn more, well, there are of course a lot of resources, but I'd maybe particularly point you to, again, the HOT book, especially the first part of the HOT book. Martin Escardo has some very nice lecture notes online that take place in AGDA plus the univalence axiom, so you can check those out and follow along if you're interested. I'd also encourage you to just play around with cubical AGDA or RedT2 if you want. The next version of AGDA is actually coming out in just a couple days. And that's really good because it fixes a lot of bugs with the cubical implementation that were in the previous release. So in a couple days, you can check out the cubical AGDA library without having to build the development version of AGDA from source. So I'm really excited for that. Anyway, that's all I've got. Thanks for listening.
Hey, thank you so much, Carlo. That was fantastic. I'll open the floor up to questions, but before I do so, I just want to mention two custodial things. First of all, if any of you either watching live or after the fact are in the peculiar position of understanding this material, but being confused about the Unetta lemma, we had Tyler Bryson on a few months ago, and he wrote some really beautiful slides on the Unetta lemma, which are available on our website. So I highly recommend checking those out. The other thing is related to the sequel paper that was mentioned. I know that the LangSec community is quite interested in homotopy type theory. And if any of you are mathematicians looking for people in computer science to possibly collaborate with in kind of applications of HOT, LangSec is an interesting place to look. Anyway, with that, I'll open the floor to questions. And if any of you have a question, please just unmute yourself and ask, and we'll do our best to not trot over each other with the delay in Zoom. Thank you. Or alternatively, I can kick us off with a question. Carlo, can you tell us just in a very concrete sense, some examples where if I'm, say, doing Adam Chapala's homework in Coq, how my life would be made easier by being able to import some of some cubical homotopy type theory?
Yeah, that's a good question. So, well, first of all, let me say that, I mean, people have developed ways of using proof assistants that try to navigate around all these landmines. Adam in particular is sort of, very good at figuring out how to sort of do something in Coq while sort of navigating around all the things that are not good about Coq. So maybe one way to look at it is it's a way of sort of more directly writing things down. So let me give you an example. There are a lot of quotients. So I talked about quotients. And sometimes you can define a quotient even if you don't have quotients because you can look at the normal forms of things. So an example of this is if you have like the rational numbers, you can't literally define, like in normal type theory, you can't literally say that the rational numbers are like, an integer and a natural number, and you take these things modulo like cross multiplication. But sometimes there is no normal form. So if you want to formalize the untyped lambda calculus modulo beta or something like that, that's you can't write down a type like in normal type theory. You can't write down the type of like terms in the untyped lambda calculus modulo beta because there are no normal forms for that. You could do something else, like you could write down a setoid where you have, the terms modulo nothing, and then you have a relation that's beta equivalence, or, there are various things you can do, but you can't like directly obtain like the untyped lambda calculus. So, with a hit, you could just obtain the untyped lambda calculus. Maybe that's like a very simple example.
Yeah, actually, Adam gave us a lecture in his class. I just sat in on his class, and he gave us a lecture recently on a reification technique. That's what he called it. I'm no whiz with theorem provers, so I might mess this up. But it really seemed kind of similar to the material here because we had some very complicated type where we wanted to prove something about it, but there were like a million edge cases. And we proved a reification lemma that sort of lifted us to a much simpler type where we only considered the data we cared about and nothing else. And then we proved our theorem about that lemma, and we proved that the theorem respected the like lifting from one type to the other. And it seems like if you had all sorts of equivalencies kind of easily pre-programmed or easy to prove because you have good tactics for equivalencies, this type of thing could be made a lot easier. Is that intuition good? Or am I way off?
Yeah, no, I think that's right. I mean, more generally, there's sort of a so when I alluded to like you have to be careful about H levels, you can sort of see a lot of complicated things in math as some sort of like coherence theorem. which says, I have this thing, and maybe it has some complicated structure, but in fact, I can show you that it doesn't have complicated structure. Or like I can show you, in fact, it suffices to only check this and this. You don't have to check all these other things that a priori you might think you have to check. Like that's, so that's a very sort of common, like, pattern just in all of math, but it especially comes up when you're in this sort of higher dimensional setting, because there's more coherence you have to worry about. So like I was saying, you have to be careful about how you define isomorphism, so that the things I was saying are right. You have to choose a definition of isomorphism that makes sure that the property that a function is an isomorphism is an H-prop. Otherwise, in fact, if you stipulate the univalence axiom, but use a non-H-prop version of isomorphism in the definition, it's actually inconsistent. So, you have to be very careful about that kind of thing.
So I probably have this is probably a silly question, but back when you were talking about how to implement hot, you said that like in Coq Agdeline, they basically wind up with like these stuck terms, I think you said. And so I guess there's sort of this hovering question in my mind of, well, if you just took this transport and inverse transport and made that like a first class citizen in the language, would that just, I mean, like, does that get you 90% of the way to like encoding hot in your theorem prover? Or is it something where like that, yeah, I mean, yeah. Like what does it take beyond just like these like I guess not what does it take to sort of beyond just like accounting for these stuck terms in Coq Agdeline to get a hot based theorem prover?
Well, so you can get a hot-based theorem prover just by adding these constants. So the problem is, like I said, you get these stuck terms. So basically the thing you have to fix is you have to add more stuff to the language so that you can actually say, well, now that I have all this extra stuff in my language, transport, well, here's what it does, blah, blah, blah. Like here's the definition of transport inverse. And that's what, so cubical type theory basically adds more stuff to the language so that you actually can implement both univalence and hits.
I see. Okay, cool. Thank you.
Carlo, what happens to the secluded middle? This term I hear people use for smarter than me. What am I supposed to know about it?
Yeah, so, okay. So, yeah. So excluded middle is the idea that if you have a proposition, it's either true or it's not true, which means if it were true, then false would be true. Right? In normal type theory, you could assert this for types, but that would be a bad idea. You can assert it for props, and that's okay. It's not constructive, which means that you don't have a way to run this function. The reason why you don't have a way to run this function is if you did, then you could say, okay, I've got a question for you, wise guy. Does this Turing machine halt? And you'd have to tell me that it halts or it doesn't halt. So you can't actually implement this function in general. You can implement it in a lot of specific cases, of course. But in hot, let's see, what am I trying to say? If you take the version for types and you also have univalence, this is actually inconsistent. But if you assert it for H props and you have univalence, this is perfectly okay. So yeah, so basically that's that's my answer. That this is sort of a non-constructive principle, which means you can't implement it as a function. But as long as you only ask for it to hold for propositions, which is the version that makes sense, it is consistent with hot. If you ask for the version that doesn't make sense, it's consistent with normal type theory, but it's inconsistent in hot.
Hello. So I was wondering, can you give some intuition as to why excluded middle for types with univalence, why is that inconsistent?
Yes, I can. So right. So basically, if you try to apply this function, let me call it f. If you try to apply this function to not just a proposition, but to an arbitrary type, then anytime you apply it to, say, well, let me apply it to bool. Okay. Well, it certainly can't give me a proof that, it can't give me the right side of the sum, because that would say bool implies false, which is not true. So it's going to give me something in the left side, which means it's going to give me an element of bool. So maybe it gives me true. I don't know. Maybe it gives me false. I don't know. It gives me one of those two, okay? And the problem is, since I have a function, so this gives me some sort of function from bool to bool, but I can actually cast it along the proof that bool equals bool by the negation function. And using some properties, some sort of easily checked properties of univalence that I didn't talk about, you can basically see that whatever f of bool does, that if you take f of bool and you cast it along the fact that bool equals bool by swapping the two things, then what this has to do is it has to give me the opposite of what f of bool gave me. So if f of bool gave me true, this one has to give me false. But on the other hand, it has to give me the same thing because it's still f of bool. So I don't know if that made sense, but basically the idea is if I pass in a type that has more than one element, then you're basically saying, I have a way of, given any set, I can give you an element of this set. So it's not just excluded middle, it's really like a global choice function that if you give me any set that's not empty, I can give you an element. But there's of course no way of giving you an element of every single set that exists that is invariant under isomorphism, because I can give you the set and you pick out an element, and I scramble the same set and I give it to you again. You can't pick out the same element because there's sort of no consistent way to sort of pick out random elements that is invariant under isomorphisms of things. I know that was not like precise, but hopefully that sort of gives you an indication. The reason why it's okay with HProp is that, well, I don't know where your procedure is coming from, but it's perfectly consistent to say anytime you give me a set that only has one element in it, I can give you an element of that set. It's sort of coming out of nowhere, like it's a magical process that's giving you an element where you didn't know where to get one. But I can never sort of do a gotcha with you where I like, now you have to pick some different element because there's only one element. So it's like A-okay.
I see. So would excluded middle for types, is that kind of like axiom of choice?
It's like a it's an even better axiom of choice that doesn't make sense. Yeah, I mean it's stronger than axiom of choice.
Okay.
Well, it depends. Okay, the same way excluded middle, you can kind of write it down in a number of different ways. Some of them make sense and some of them don't. You can write down the axiom of choice in several ways. Some of them are just automatically true in normal type theory. Some of them don't make any sense. Some of them are consistent. So yeah, I mean, it depends. As always, it sort of depends on how you choose to render these statements. But yeah, it is related to choice. Yeah.
Carlo, I'm confused about something really dumb. We had two paths for bool. One of them was the ID and the other one was the not function. Why was it that the function that maps everything to true or that maps everything to false, why those two did not count as paths?
Oh, because that's not an isomorphism,
I see. Okay, that makes sense.
right? Yeah.
Yeah.
Because you can't invert sending both the points to true.
Yeah, of course. Thanks.
I have a question.
Mhm.
It's actually about cubical AGDA because I haven't used it yet, but I've seen people using it, and the proofs looked like they were very complicated and long in comparison to regular AGDA proofs. Is that like a thing? Is it still because like too early in the implementation, but in the future it might be more ergonomic to use cubical AGDA?
So I guess it's sort of hard to comment without knowing exactly what you're talking about, but I'd say that, I mean, first of all, yes, cubical AGDA is new, and we're, it's like I said, it's the new release of AGDA is going to be like way better than the previous one. But I mean, everything in normal AGDA works, or okay, maybe not every flag, but all the sort of stuff in normal, in like core AGDA also works in cubical AGDA. So you can't really be in a situation where you had a simple proof before and now the proof is really complicated, because the old proof will still work. But I mean, maybe one symptom or one reason why it looks more complicated is that the cubical AGDA library is a lot of it is devoted to like some very complicated like synthetic homotopy theory and stuff like that. So yeah, so the proofs of those things are going to be kind of gnarly, and also we're getting better at using cubical type theory, as time goes on. So like we'll be able to figure out better proofs and so on. But yeah, I guess I'd just say that for the really so the way that cubical type theory works basically is that it gives you a bunch of combinatorial stuff that lets you write something down here for the implementation of univalence, for example. And if you want to get your hands on, like, do that combinatorics by yourself, you can do it, but it will start to get pretty complicated. So like sometimes the intermediate states of computations will look pretty complicated because they're involving like high dimensional objects. But hopefully, at least, the idea is like when you're sort of driving things down to base type, then they will look simple. So I don't know. Oh, maybe that helps a bit.
Yeah, that helped. Thank you.
Carlo, there's a question in the chat. Julia is wondering, is there anything undecidable in cubical AGDA and such?
So I mean, you can definitely write down propositions that are undecidable. I mean, the same way you can in like any logic. So I'm not sure if I said this, but the sort of symbolic execution of programs done by a type checker, usually we require that to be a decision procedure. That the type checker can tell for sure whether two terms are the same up to that very strict equality, or if they're not the same up to that equality. And it is true that the judgmental equality or the strict equality in cubical AGDA is also decidable in that sense, or it is supposed to be decidable in the sense that it can tell whether two cubical programs are like symbolically execute to the same thing or not. But the weak equality, the sort of path equality or identity type, that cannot in general be decidable, because again, that gets you into like, you can sort of reduce everything to asking whether two things are the same in some weak sense, and it's so that can't be decidable. Yes, yeah, okay. Someone asks, in a nutshell, why is cubical AGDA a compiler flag instead of just a library? Well, yeah, so because it has to, you actually have to add sort of more programs. You have to add new kinds of programs to the language to be able to write down the definition of univalence, for example. And one way to see why that's the case is that if you don't have univalence, it's actually it's independent of the language. It's not a consequence of normal type theory that univalence holds. So if you don't add anything new to type theory, you can't sort of define a function that implements univalence. Does that answer the question?
Yeah, it answers it a bit. I was thinking of functional extensionality. So for example, in Coq, you can just import this module and you're good to go. So it doesn't really need to add some compiler or the language support. So here it's different because it's, I don't know, is it more invasive in a sense?
Well, so the Coq library for function extensionality, adds a postulate that says function extensionality holds. So similarly, yeah, if you just want to take Agda and add postulates to it, or Coq and add postulates to it, you can do that. But then without like changing the theory. The problem is then you can't sort of simplify anything to use those postulates. So the reason why cubical Agda is like complicated is you have to actually add features so that Funext and univalence just like are true. So that actually requires like changing the core theory of the proof.
Cool. Yeah, I had another question actually. So the proof that bool is isomorphic to itself, there are two proofs as you mentioned. So it was the case in the sort of classical dependent type theory. So how does adding univalence change this fact? Does it even change it, or like how does it change my life after the fact that
right. So what it does is, so I mean you always have there are two isomorphisms between bool and bool, but you don't normally have that this gives you multiple proofs of bool equals bool. So you don't normally have this inverse. Now maybe you would ask like, well, why do I want multiple proofs of bool equals bool? Well, yeah, I mean it's sort of hard to answer that directly. I think what I'd say instead is like the fact that you end up getting an isomorphism here ends up giving you other universal properties that are good. So for example, with a propositional extensionality, when you have univalence, it implies that, well, you can always show that if you have two propositions, sometimes you can show that these propositions imply each other. Okay, so that's just something you can do or you cannot do depending on the situation. But what univalence tells you is that then anytime I have some theorem involving one of those propositions, I can cast it to be a theorem about the other proposition instead. And that's not something that in normal type theory you don't have sort of for free, the fact that anything that's true about P is also true about Q if P and Q are interprovable.
Right.
Yeah.
Makes sense. Thank you.
Okay, I think we should maybe just take one or two more questions and then wrap up because we're at the hour. Or we can just wrap up. Carlo, thank you so much for talking to us. This is really phenomenal. I certainly learned a lot. Other people might have learned less if they knew more than I did in the first place, but regardless, I'm sure everyone enjoyed the talk. I will be making this available on probably YouTube. I haven't 100% decided yet in the next few days. So if people want to go back and review, or if, for the future, if people didn't watch this but want to, they will be able to, as long as I can trust the icon on the top of the screen that says recording. Hopefully it worked. We host talks like this pretty frequently on all sorts of topics. In a couple of weeks, we're going to have my friend Maria Lenore from Purdue come to talk about natural language processing. We have a talk from a well-known journalist about algorithmic policing after that. All sorts of things in the pipeline. So you can check out our website. I also post about stuff on Twitter. And so we're easy to find. If you'd like to attend talks, just shoot me an email or something and I'll add you to the Slack. Carlo, thank you again for talking to us. This was superb. And we really appreciate your time.
Yeah, thanks for having me. Yep.
All right. Adios, guys.
Okay. Bye.